essentially to tie each other, a game of chicken. They tied themselves to the wheel, to the steering wheel. They thought that doing that would make them step on the brakes and come to an agreement, but they actually didn't, so they went over the cliff. And the cliff was the sequester that said, we're just going to cut across the board a certain amount of money from the federal budget. Kind of a dumb way to do it. But look what's happening in spending, and we know that there's a relationship between that spending and in particular green jobs. So this stuff matters from that way. Here's another green job, in a sense. These are firefighters. Their budget comes from the Forest Service. Why are they fighting fires? Do you know where they're fighting a fire? It's a really recent photo. Where was it? Yes, the Rim Fire in Yosemite in California. This is one of the biggest fires. You take a fire-prone area, you fight fires for a long time, you let people build houses in places that are meant to burn, that's the forest ecology, and you keep it from burning, and then you need to protect those houses, so you take your budget away from anything else the Forest Service does, and you put it into firefighting to protect these houses out in a tinderbox. This is a view from space of the Rim Fire using a 50mm lens. 50mm is essentially just like your natural eyesight. Here's the Rim Fire, all of that. This might have to do with the fact that it's hotter and drier in California than it used to be. This is a view of New York, almost a year ago. Superstorm Sandy. That looks like out of a science fiction movie. Well, okay, you can't see it's dark because the point is that it was dark because they lost power. So when the climate impacts a whole bunch of people living in buildings, right, all in one place, you get a huge impact on these people. Here's flooding in the city. Just all the roads. That's the Brooklyn Bridge is closed. I mean, the tunnel's flooded. And then you've got combustible fuels stored in houses or on pipes going to houses, and you throw nature at them really hard. Sometimes things go kaboom. So that's one impact we've had. But also Texas, for example, this is the third straight year of extreme drought. This was in June. This was a picture of the United States drought. The redder it is, the worse the drought. That's pretty bad. If you look at precipitation, there's a lot less precipitation. So less than normal precipitation. You know, the redder it is, the less precipitation. A lot less in the spring. Any surprise there's a big fire? But it's not just that. If you take the precipitation out, okay, and you just look at the evaporation index, so this is how much is evaporating out, and you just take out the amount of precipitation, what you see is there's a lot more evaporation. You can see a trend there, right? In other words, it takes more rain to make up for the more rapid evaporation. Why is there more evaporation? Because it's hotter. So here's the seasonal drought outlook at the beginning of summer. Basically, it was either going to continue to be drought, or you were going to get drought where you didn't have it. A few little green bits where it was going to actually stop being drought. Climate change is real, and it's worth kind of understanding. This is why I'm motivated to think about this stuff right now. So you can see average temperature goes up, average sea level's going up, snow cover's going down. You can see that the model projections for each of these kind of general areas are basically right. So the blue is what the world would look like without human-introduced carbon dioxide levels, essentially. That's what the weather would be according to these models. You take the same model and you say, let's slug it with the human-generated carbon dioxide. The black line is what actually happened. The red line is what the computer says, the computer model says would be about what happened. You see that the models tend to get it. So we're getting the rapid loss of sea ice as predicted. And now this isn't going to raise sea levels on its own. This, you know the analogy: you put a ice cube in a glass of water. When it melts, it's not like the water overflows the glass. But this is going to relate to a lot of physical principles we're going to talk about, because there's going to be less albedo, so less reflectance of the sun's energy. More of it's absorbed into the water, and which is another thing that we can think about, which is the water's ability to absorb and re-radiate heat at a later time, in this case, decades later. It is what we'll call a thermal mass, and we're going to talk about thermal masses a lot in dealing with especially kind of passive design. Sea level's been rising, and essentially as predicted. We also are getting more water where we don't need it, say New York City, and less water where we do need it, say Yosemite. And these are up there. You can look at some of the indicators. But it also has a big implication for electricity production, because we do a lot of hydroelectric electricity production. Heat waves are going to be more frequent. That's going to matter for housing, right? If we build houses that are not energy efficient, they're going to take a lot more energy to keep them cool. And so this is kind of all the years from 1909 to 1864 to 2000, and you can see the mean temperature was, a nice cool, 17 degrees Celsius. That's what, 66 degrees Fahrenheit, something like that, roughly. The projected median for an entire year, which means that you're going to have heat waves way up here. Projected median is around, looks like 21, which is about 70 degrees Fahrenheit. But remember, that's an average for an entire year. So less cold, more heat. And so New York would be getting well over 100 degrees as an average temperature in the summer, with global warming of 4.6 degrees Celsius, whereas if we can keep it below 2 degrees Celsius, which is kind of the internationally agreed upon goal, it stays in the 80s as an average temperature. That's pretty good. So, anybody seen this graph before? This is called the Keeling curve. Basically, David Keeling went up to Mauna Loa in Hawaii and recorded carbon dioxide levels, concentrations in the air. And it's just, you can see the pattern. We've been recording those levels. We haven't actually crossed 400 parts per million. There was a lot of news this summer that we had. It was just a blip. We haven't. Next year we will. Okay? So that's the path we're on. This curve up. This fluctuation is about, it's an oscillation as the seasons change. That's what that is, northern hemisphere. How many years, does anyone know how long carbon dioxide stays in the atmosphere, roughly? Anyone got a guess? If I emit a mole of carbon dioxide now, how much will, how long until that mole is gone? 50 years? 100 years? 500 years? Well, here's the pattern, okay? You emit it, okay? And very quickly, about 40% of it's going to actually get recovered on an annual basis by trees and stuff. And then over the next 2,000 years, about 25% of it will get absorbed by the ocean. And then you've got 25% left. Now over a much, much longer process, a 10,000-year long process, it weathers with rock and gets out of the atmosphere. And then we have about 10%, which is going off into the 100,000s of years to get weathered with rock. So this is a different thing than when we talk about these goals, right? About 100 years. We talk about by 21,000, this is this is what the temperature could be. This is what the parts per million of carbon dioxide could be. Okay. Look what happens. So the gray line is if we decided right now to really dramatically reduce our carbon dioxide emissions up on this upper line. Okay. The black line is if we burned every single bit of coal in the ground. We're not going to do either of these things, right? We're going to be somewhere in between there. If we do that, right, we can, by the middle of the next century, our emissions go to 0. Okay? That's on this best of all possible cases. And in the middle of 4 centuries from now, our emissions go to 0 if we do the other path, which we're not going to do either one. But look what happens depending on which path we take as to the concentration, right? We're near 400 parts per million now. And we actually could get back to a concentration of around 400 parts per million. In other words, weather kind of like ours by, you know, what's that? 3,000? The weather, right, could be like us now, or it could be insane. So this is the time scale we're thinking about. And that means we need to deal with the fastest path to 0. And I'm going to try and make the argument that housing, in particular, and buildings in general, housing in particular, are the biggest portion of that fastest path to 0. And we need to think about 3 reactions to this, okay? Because there's actually good news. Unfortunately, I'm not going to have time to tell it to you today. A kind of bit of a downer, right? So we can adapt, right? The climate is changing. We are not in an old climate. We're in the new climate. We're in a climate that actually is changing as we go. That, for your lifetime and your grandchildren's lifetime, is going to be a climate that's always changing. It's not going to be stable. It's roughly, you could argue that that's kind of been all of human history, just not this fast. So we're going to have to adapt to that. That means we need to build structures that can adapt within an individual's lifetime to these changes. And adapting structures and adapting infrastructure. We need to mitigate. So mitigate is to not emit carbon dioxide and to capture carbon dioxide, right? And other greenhouse gases. But we need to kind of do something about this problem to slow it down. So that's mitigation. And obviously, anything that saves energy is going to play a big part in mitigating. And then we also have to prepare for this new climate. So be prepared for sea level rise. Be prepared for droughts that last a generation. What do we do? I don't know all the answers, but by acting as a community to prepare for these, we're actually going to kind of take care of a lot of this stuff. And that's where the opportunity is. But it's also the end of, no, I've got 5 minutes. Well, in that case, that's where the opportunity is. We have, you know, housing can play a really, really big role in this. And that's why I care about this stuff. We've got all these challenges, right? So if we use less energy, we can spend more money on something else. We have more money. If we use less energy, then the entire electricity grid can be more nimble. It doesn't have to be subject to as many disruptions. I don't know, it was 10 years ago, 2003, the entire East Coast went black because a tree fell on a utility pole in Ohio. We can fix our grid. We can do it better if we have more money for that and less for just generating electricity. So we're going to have these bigger, more frequent storms. So we need to build tougher houses, basically, and we need to build them in the right places. And we need a better environment. This thing creates a better environment, right? We have more hot, more humidity. We have more pathogens and pests. That means we need to do better with indoor air quality and outdoor air quality. And we need to do better with how we interact so that, you know, from a public health standpoint, and buildings have a huge role to play with that. Where are people going to go? It's going to be too hot to live in Phoenix. Where are they going to go? And there's obviously reduced arable land when there's areas where you no longer can farm. We're already seeing that in the greater Midwest. But we have these worst scenarios that we can deal with, right? We can avoid resource wars. We can avoid food scarcity.